Welcome. This is the progress report 2 for my mechanical behavior of materials project, which is the structural and thermal analysis of automotive disc brake rotor. So just a quick recap. The disc brake is a device used for slowing or stopping rotation of a wheel. The repetitive braking of the vehicle leads to heat generation. So I'll be doing a steady state thermal and a structural analysis of the rotor disc, the disc brake. This analysis is aimed at evaluating the performance of the disc brake rotor of a car under severe braking conditions, and it thereby assists in the design and analysis of the disc brake. The analysis will be carried out for a ventilated disc brake for different materials, and the results will be compared, thereby allowing the selection of the optimal material for this brake. So moving on, this is the geometry of the ventilated disc brake that I've selected. As you can see, I've modeled the disc brake in SolidWorks and I've done a quick rendering. As it is clear from the rendering of the disc brake, you can see that there's a gap in the middle of the two discs, and hence this is a ventilated disc brake, as you can see over here too. And you can also see that on the faces over here, a number of circular and long vents have been provided. This is to dissipate the heat which is generated during the braking. To make the design clearer, this is an engineering drawing of the ventilated disc brake. As it is clear from the drawing, the outer diameter of the disc brake is 180 mm and the inner diameter is 104 mm. So everything in the middle of these two diameters is the working area of the disc brake, where the pads are going to hold the brake, thus applying the braking force. It's also clear from the drawing that the width of the disc brake is 15 mm. So this is the project schematic, which is essentially how the the analysis has been carried out in the project. So as you can see from the first module, steady state thermal analysis was done first in the disc brake, and once we got the results for this, the model data for this was shared with the module for the static structural analysis. It can be seen over here. Yes. And also the solutions derived from the steady state thermal analysis were shared with the setup for the static structural analysis. This was done to show the effects of the temperature which was generated in the steady state thermal analysis on the deformation and the stresses which were induced after the static structural analysis was done. So now we move on to the materials. The materials I've considered for this analysis are the materials which are used in the real world for manufacturing the brakes. So I've gone with 4 materials, which are stainless steel, titanium alloy, cast iron, and aluminum alloy. So this is to give you a quick rundown of the analysis settings. So the temperature which was taken for this thermal analysis was around 500 degrees Celsius. And the mass of the vehicle was assumed to be around 1385 kgs. The time required for stopping the vehicle was 45 seconds. Now the effective diameter of the brake pad, which I've already shown in the engineering drawing, is around 180 mm. Now the formula for the braking force is given by this formula right here. So after plugging in the values, I derived the braking force to be around 1047.36 Newton. So for the sake of simplicity, I applied a force of 1050 Newton on the face of the brake pad, which is shown here in this image. So the red face is where I applied the braking force. So now we'll move on to the deformation and von Mises stress contours derived for the braking pad for different materials. We'll be starting with the stainless steel. So the left hand side contour shows the deformation which is derived for stainless steel brake pad, and the right hand side shows the stresses induced. So as you can see over here, the deformation is mainly located at the outer rim of the brakes, whereas the stresses can be found to be concentrated near the hub. So the 5 holes you can see near the hub, which will be connecting the wheel, is where we mostly find the stresses. So these 5 holes were given a fixed support in static structure analysis before the force was applied. So next we move on to the deformation and stress contours for cast iron. As you can see, compared to the previous one, which is right here, stainless steel, the deformation has gone down, and so have the stresses. We see this trend also for titanium alloy. As you can see over here, the deformation has gone down further, so have the stresses. And Now for the last contours, which is for aluminum alloy. As you can see over here, that we get a higher deformation, but the stresses have reduced further. So now these two tables show you the comparison between the deformation and the von Mises stresses for the different materials. As it is evident from the two charts, the deformation and the von Mises stresses are the least for titanium alloy, followed by cast iron in both the cases. So in inference, I would say that titanium alloy is the optimal material for the design of the disc brakes, but it is slightly costlier than the other materials which are considered. So for the next step of the project, I would be analyzing the disc brakes for both titanium alloy and the material which is closest to it in properties, which is cast iron. So here the next step in my project would be to perform the static structural analysis of the disc brake for titanium alloy and cast iron, as I told you in the earlier slide, with fatigue tool to check the life and the damage which is being induced in the brake due to the cyclical nature of braking force and also the heat generated because of this force. As you can see from the stress contours, the hub of the brakes shows the real concentration of stress. So I think this area can be further strengthened to avoid fatigue fracture and other damages. The fatigue analysis tool will help to determine the failure due to the fatigue, which can occur at loads which are much lower than the ultimate tensile stress of the material.